It begins in silence as it always does. Space is vast, but it is not empty, and our digital eyes are finely sharp enough to see the travellers hiding in the dark. In the summer of 2025, a small automated observatory flagging objects near Jupiter's orbit catches something unusual. It's moving too fast. Its trajectory is wrong. The computers calculate its path backward, tracing its origin not to our own Kuiper belt but to the black cold space between the stars. It is an interstellar visitor. This isn't the first. We had Oumuamua, a strange cigar. We had Borisov, a mostly normal comet from afar, but this new object is different. It's larger and it's active. It is outgassing venting material as it warms near our sun, creating a temporary atmosphere, a coma that we can actually read. Every major instrument on and off Earth turns to look. The schedule of the James Webb Space Telescope is frantically cleared. In early August, Webb stares at the traveller. It uses its powerful infrared sensors to split the light coming from the object's coma, looking for the chemical fingerprints of the gases. The data comes back. The astronomers who see it first do not celebrate. They check the instruments. They run the calibration again. They are silent. The public sees graphs and charts. The news reports talk of a spectacular visitor from another star. But in quiet laboratories and secured video calls, a single spine-chilling fact is passed between scientists. It is the core of the data. It is the reason for the silence. The fact is a number. It is the ratio of gases found in the object's plume. In our solar system, comets are dirty snowballs. They are mostly water ice. They have some carbon dioxide, what we call dry ice, but water is always the dominant material. The new visitor is not a dirty snowball. The James Webb data is undeniable. Its plume contains 8 parts carbon dioxide for every 1 part water, an 8:1 ratio. This is not just unusual, it is physically screaming. It is a signature that does not exist in our understanding of natural comet formation. A comet from our system might have these gases in reverse proportions. This object is venting the chemical signature of an industrial process. It is the profile of massive-scale exhaust or the atmosphere of a planet that has been technologically altered, frozen, and shattered. The object isn't just a rock, it's a message. It is a whisper from the void that says we are, or perhaps we were. And this brings us to the true subject. It is not the object itself, but the human reaction to it. We are faced with the most profound data point in history, and we have collectively chosen to miss the point. This is the communication gap. This gap is not a conspiracy. No one is hiding little green men. This gap is more subtle and more dangerous. It is the chasm between what the data says and what we allow ourselves to hear. The official papers will be published. They will use words like anomalous, peculiar, and presenting a challenge to current models of planetesimal formation. This language is technically accurate, but it is not true. It is a failure of courage. It is the scientist's instinct to be so cautious, so precise, that they refuse to name the animal standing in front of them. When the data shows an 8:1 ratio of carbon dioxide to water, anomalous is not the right word. Artificial is the right word. We are not just failing to communicate with potential outsiders, we are failing to communicate with ourselves. We are reading between the lines of our own scientific reports, too afraid to say aloud what the numbers clearly imply. The communication gap is the sound of humanity politely ignoring the sound of a knock on the door, hoping it will just go away. But it is not going away. The object will pass. It will sweep around the sun and be flung back into the interstellar dark, but the data remains. The fact of the 8:1 ratio remains. It is a permanent stain on our theories of solitude. This is why we are here. You have felt this gap. You have seen the official reports and felt that something vital was being left unsaid. You are right. We are going to close that gap together. We are going to pull back the curtain. This is not a journey into fantasy. It is a journey into the hard data that everyone is too polite to discuss. We will look at the numbers, the physics, and the deafening silence from those who know better. We will examine what that 8:1 ratio truly means, not what we wish it meant. The whisper from the stars has arrived. The curtain is lifting. We must be brave enough to see what is on the other side. The decision to point the James Webb Space Telescope, or JWST, at Comet 3I Atlas was not a casual one. This telescope is the most powerful and complex observatory ever built by humans. Its time is scheduled down to the minute, with thousands of scientists from all over the world competing for just a few hours of observation. Giving this comet time on the glass meant that the scientific community already knew it was profoundly important. It was a chance to study a pristine messenger from another star system up close, and no one wanted to miss it. What JWST found, however, was more bizarre than anyone had anticipated. The telescope's sensitive instruments can taste the chemical fingerprint of the gas boiling off a comet. The standard model of comets, based on everything we know from our own solar system, is simple. They are dirty snowballs. They are composed overwhelmingly of water ice. When a comet approaches a star, the ice turns directly into gas, creating the fuzzy head, the coma, and the tail. Other ices, like carbon monoxide or carbon dioxide, are almost always minor ingredients, making up perhaps 10 or 20% of the gas. JWST's analysis of Atlas shattered this model. The data was clear and unambiguous. The comet was not dominated by water, it was dominated by carbon dioxide. The ratio was shocking. For every 1 part of water ice turning to gas, the telescope detected 8 parts of carbon dioxide gas. This was not a dirty snowball, it was a dirty dry ice ball. This single finding effectively reversed our most fundamental idea of what a comet is. Water was not the main component, it was just a minor trace. This observation sent a shockwave through the planetary science community. A comet so rich in carbon dioxide and so poor in water was simply not supposed to exist. It meant Atlas must have a very strange origin story. Immediately, scientists scrambled to come up with explanations. 2 main official theories emerged to explain this bizarre 8-to-1 ratio, and both of them paint a picture of a comet born in an extreme and unusual environment. The first hypothesis is the ultra-cold birthplace theory. In any forming solar system, different ices can only freeze at specific distances from the star at a point called the snow line. Water ice can form relatively close to the star, just beyond where rocky planets like Earth form. But carbon dioxide needs much colder temperatures to freeze into a solid. This theory suggests that Comet Atlas formed in a super deep freeze region of its home star system. This would be a place much farther out and far colder than the zones where our own comets formed, like the Kuiper Belt or the Oort cloud. In this intensely frigid darkness, perhaps carbon dioxide ice was the main building block available, making it the dominant material from the very beginning. If this is true, it means Atlas comes from a type of planetary nursery that is incredibly rare, or at least one we have never had a sample from before. The second hypothesis is the violent processing theory. This idea suggests that maybe Atlas did start as a normal water-rich comet, but then it suffered a catastrophic history. Perhaps it spent millions of years passing too close to a blazing hot star, or its own parent star went through a violent phase, blasting its system with intense X-rays and ultraviolet light. This hard radiation would have acted like a sandblaster. Because water ice turns to gas more easily than carbon dioxide, this violent radiation could have stripped the comet of its outer layers, boiling away almost all of its water ice over eons. What we are seeing today, according to this theory, is not the original comet, but its processed core, a dense leftover nugget that has had all its water effectively cooked off. Here is the key takeaway. It does not matter which of these 2 theories is correct. Both of them force scientists to the same conclusion. Whether it was born in an impossibly cold place or was violently stripped of its water comet 3I Atlas is a true outlier. It is not like other comets. It is an alien in the truest sense of the word, and it breaks our models. But JWST was not done adding to the puzzle. Its instruments also looked at the type of ice, not just the gas. It found 2 more fascinating clues. First, the ice grains being blown off the comet were incredibly tiny, measuring less than 1 micrometer across. This is smaller than a particle of smoke and is best described as a fine, fluffy powder. This suggests the comet's material is very loosely packed, almost like cosmic fairy floss. Second, and perhaps more importantly, the telescope detected amorphous ice. This is a crucial clue. The ice in your freezer at home is crystalline, meaning its water molecules are locked in a neat, orderly, strong grid. Amorphous ice is the opposite. It is shapeless, with its molecules jumbled in a complete mess. This type of disordered ice can only form and exist at extremely cold temperatures below about minus 173 degrees Celsius. If it had ever been warmed up even slightly, the heat would have given the molecules enough energy to snap into their preferred orderly crystalline shape. The discovery of amorphous ice is a smoking gun. It proves that this comet is absolutely pristine. It has never been heated. It has never passed close to its own star. It is a preserved relic that has been in a deep freeze since the moment it was born, which strongly supports the ultra-cold birthplace hypothesis. Just as this picture was coming into focus, a fluffy, cold, carbon dioxide-dominated object, another spacecraft, delivered a final contradictory puzzle. Data from the Swift Observatory, which looks at ultraviolet light, did detect water, but it detected it in a way that made no sense. The water was turning to gas at an enormous distance from the comet's solid body or nucleus between 4,000 and 10,000 kilometers out in the fuzzy coma. This created a massive paradox. How can water be evaporating thousands of kilometers away from the comet ice needs to be heated by the sun to turn into gas, and that should only happen right at the surface of the nucleus? This finding contradicts the JWST data, which found almost no water at the core. It suggests the water is coming from the fluffy, tiny ice grains that were blown off the core earlier, but this just deepens the mystery. The data from Atlas was not providing answers, it was just piling up the anomalies. We were faced with a comet made of carbon dioxide, yet somehow sprouting water far from its body. It was made of pristine, fluffy, super cold material, yet it behaved in ways that defied physics. Atlas was not just a visitor, it was a riddle that challenged our most basic understanding of how solar systems are built. The physical drama of 3I Atlas tearing itself apart was a breathtaking spectacle, but for scientists the real treasure was the ghost it left behind. As the comet disintegrated, it released a cloud of gas and dust offering a pristine sample of its inner composition. Using the powerful tools of spectroscopy, which analyzes light to determine what chemicals are present, astronomers peered into this cloud. What they found was not a simple familiar object, but a complex chemical zoo, a collection of ingredients that painted the portrait of a truly alien visitor. One of the most staggering discoveries came from SphereX, which detected an enormous cloud of carbon dioxide gas billowing away from the comet. This cloud was measured to be a mind-boggling 348,000 kilometers across. To put that in perspective, this single cloud of gas was vast enough to almost span the entire distance from the Earth to the Moon. Carbon dioxide, familiar to us as dry ice, is a common ingredient in comets within our own solar system. However, the sheer size of this cloud was monumental. It suggested that 3I Atlas was incredibly rich in carbon dioxide ice. This is significant because carbon dioxide ice turns to gas, a process called sublimation, at much colder temperatures and farther distances from the sun than water ice. This enormous carbon dioxide signature helped explain why 3I Atlas had brightened so dramatically while still in the cold outer solar system. It was being driven not by water but by a massive outgassing of carbon dioxide like a cosmic dry ice bomb. But the chemical surprises were just beginning. The powerful mirrors of the Very Large Telescope VLT in Chile were aimed at the fading object, and they detected something incredibly exciting: cyanide gas. While the word cyanide sounds dangerous in astrophysics, it is a molecule of profound importance. Cyanide is an organic compound, meaning it is based on carbon. Specifically, it contains a strong bond between a carbon atom and a nitrogen atom. This carbon-nitrogen bond is a fundamental building block for more complex life-sustaining molecules, such as amino acids, which build proteins, and nucleobases, which build DNA and RNA. Finding cyanide in a visitor from another star system is a powerful piece of evidence. It suggests that these crucial prebiotic ingredients, the very starting materials for life as we know it, are not unique to our solar system. They are likely common throughout the galaxy, formed in distant star systems and ferried across interstellar space by comets like 3I Atlas. As if that weren't strange enough, the Very Large Telescope detected something else that made astronomers scratch their heads: the vapor of nickel, a metal. This was truly bizarre. Comets are dirty snowballs, mixtures of ice dust and rock. Metals like nickel are heavy and have extremely high boiling points. You don't expect to find metal gas floating around a cold comet. Its presence implies that this nickel must have been heated to a very high temperature at some point to vaporize. How? Perhaps 3I Atlas passed incredibly close to its parent star in its home system, heating it intensely before it was ejected. Or perhaps the nickel was not pure, but part of a specific chemical compound that releases metal atoms more easily. Either way, finding metallic vapor strongly suggested that 3I Atlas formed in an environment with a different chemical makeup and history than our own solar system, one possibly richer in metals or subjected to more extreme temperatures. The story of its chemical volatility was confirmed by another telescope, the James Clerk Maxwell Telescope JCMT. This observatory, which studies light in the microwave part of the spectrum, was monitoring the comet's production of hydrogen cyanide, another vital prebiotic molecule similar to the cyanide found by the VLT. The JCMT's observations captured a period of intense sudden activity. In a single week from September 7th to September 14th, the rate at which 3I Atlas was spewing out hydrogen cyanide tripled. This wasn't a gentle, steady leak, it was a violent surge. This event was the smoking gun for the comet's fragmentation. As the comet's core cracked and broke apart, it exposed fresh, untouched ices from its interior to the sunlight for the first time. This pristine material buried deep inside the comet for perhaps millions of years instantly vaporized, releasing this massive burst of hydrogen cyanide. Scientists were in effect watching the comet bleed out its ancient hidden chemical secrets. This complex chemical profile allowed for a crucial comparison. The second interstellar visitor 2I, Borisov, had been a fascinating guest, but in many ways it was familiar. Its chemical makeup, particularly its high abundance of water, made it look remarkably similar to the comets born in our own solar system. Borisov's message seemed to be that comets are probably similar everywhere. 3I Atlas shattered this simple conclusion. It was profoundly unfamiliar. Compared to Borisov, 3I Atlas was water-poor. Instead, it was dominated by carbon dioxide. It contained strange metal vapors like nickel. It died in a violent explosive fragmentation. This stark difference between the second and third interstellar guests led to a profound realization: the population of interstellar comets is far more diverse than we ever imagined. This brings us to a compelling speculation. Must different star systems create different types of comets? The evidence from 3I Atlas suggests the answer is a resounding yes. A star system's comets are fossils of its birth. They are made from the specific mix of gas and dust that was present in the protoplanetary disk around its parent star. If that star system was, for example, much richer in carbon and poorer in water than our own, it would produce comets rich in carbon dioxide and dry ice, just like 3I Atlas. If its formation was hotter, it might produce bodies with more processed metals. By studying these visitors, we are engaging in a form of galactic archaeology. 2I Borisov gave us a sample from a system much like our own. 3I Atlas gave us a sample from a system that is chemically distinct and fundamentally different. Each new interstellar visitor is a postcard from an unknown star telling us about the sheer chemical diversity of our galaxy. When astronomers turned their telescopes toward 3I Atlas, they weren't just looking at a single simple object. They were opening a chemical treasure chest from another solar system. What they found inside was a bizarre collection of materials, a spectral zoo of different gases and even metals that painted a picture of a very alien origin. Each new observation added another strange creature to this zoo, revealing a profile far more complex than anyone had anticipated: the giant breath of carbon dioxide. One of the first stunning discoveries came from the Spheric Space Telescope. It revealed that the comet was surrounded by a truly gigantic invisible cloud of gas. This cloud, or coma, was not primarily made of water vapor, which is what we often see with comets from our own solar system. Instead, it was dominated by carbon dioxide, CO2. The sheer scale of this cloud was difficult to comprehend. It measured approximately 348,000 kilometers across. To put that in perspective, the distance from our Earth to the Moon is about 384,000 kilometers. This means 3I Atlas was enveloped in a cloud of carbon dioxide gas that was nearly wide enough to span the entire gap between our planet and its moon. This discovery was a major clue. In the cold darkness of interstellar space, carbon dioxide exists as a solid like dry ice. For the comet to release such an enormous amount of this gas, it must have been loaded with carbon dioxide ice, which was turning directly into vapor, a process called sublimation, as it was warmed by our sun. This suggested that wherever 3I Atlas came from, frozen carbon dioxide might be a more common building material than frozen water, a fundamental difference from our own solar system. Clues of life and extreme heat. The story got even stranger when the Very Large Telescope VLT in Chile took a closer look. By splitting the comet's faint light into a rainbow spectrum, astronomers could identify the specific chemical fingerprints of the materials being released. They found two things that were both exciting and baffling. First, they detected cyanide CN gas. While the word sounds dangerous in astronomy, cyanide is a vital molecule. It is an organic compound, meaning it's based on carbon, specifically a carbon atom bonded to a nitrogen atom. Molecules like this are the basic raw ingredients needed to build more complex structures, such as amino acids, which are the building blocks of proteins and life itself. Finding cyanide confirmed that this interstellar visitor was carrying the fundamental chemistry for life. The second VLT discovery, however, was a complete shock: the unmistakable signature of nickel Ni vapor. Nickel is a metal. You find it in stainless steel in our planet's core and in metal-rich asteroids. It is heavy solid and does not turn into a gas easily. To make solid nickel boil into a vapor, you need extremely high temperatures, far hotter than what a comet should experience even when close to the Sun. This was a profound puzzle. It strongly suggested that 3I Atlas was not just a simple ball of ice. It must have contained bits of metal-rich material. This finding opened up wild possibilities. Perhaps the comet was a fragment of a larger, more complex body from its home system, an object that was large enough to have a metallic core like a tiny planet. Or maybe it formed in a region of its solar system that was surprisingly hot, allowing metals to mix with the ices. Whatever the answer, the presence of metal vapor pointed to a violent or high-temperature history, unlike that of our own comets. A sudden, frantic outburst. This complex visitor was also incredibly active and unpredictable. Astronomers using the James Clerk Maxwell Telescope JCMT in Hawaii were monitoring the comet's output of another important organic molecule, hydrogen cyanide HCN. Like the cyanide found by the VLT, this molecule is another key precursor for life's chemistry. They weren't just measuring what was there, they were measuring how fast it was being released. What they saw was a sudden dramatic flare-up. In the span of a single week from September 7th to September 14th, the rate at which the comet was pumping out hydrogen cyanide gas tripled. This wasn't a gentle, steady melting, this was an outburst. It suggested that as the comet tumbled through space, a new pocket of frozen hydrogen cyanide previously buried beneath the surface was suddenly exposed to the sun's warming rays. This fresh patch of ice instantly vaporized, releasing a massive plume of gas. This event showed that 3I Atlas was not a uniform chunk of material. Its interior was a complex, lumpy mixture of different ices and materials all jumbled together, a tale of two visitors. To truly understand how alien 3I Atlas was, we must compare it to the only other interstellar visitor we had studied in detail, 2I Borisov. When Borisov flew through our solar system, astronomers were amazed at how normal it was. Its chemical makeup, especially its high ratio of water, made it look almost identical to the comets born in our own solar system. Borisov felt familiar. It gave us a comforting thought: maybe all star systems are built using the same basic recipe. Atlas rattled that idea. It was the complete opposite. Borisov was water-rich, just like our comets. Atlas was carbon dioxide-rich, unlike our comets. Borisov had a familiar chemical profile. Atlas had a spectral zoo of strange ingredients, including metal vapor that suggested a high-temperature origin. This contrast is perhaps the most important lesson from 3I Atlas. It forces us to ask a profound question: do different star systems create different kinds of comets? The answer now seems to be a resounding yes. Borisov may have come from a star system that evolved much like our own, but 3I Atlas must have been born in a place that was chemically and physically very different. Its star, its planets, and the leftover material that formed its comets must have followed a different path. 3I Atlas proved that the universe is far more diverse than we could have imagined. It's not a one-size-fits-all galaxy. Each interstellar visitor is an archaeological artifact from an unknown world, and this one told us that the zoos of chemicals in other solar systems can be wildly different from our own. To understand the mystery of Comet 3I Atlas, we first need to understand a basic truth about comets. They are not just passive balls of ice and rock. They are active. They are in a very real sense mini-rockets. This rocket-like behaviour is a core concept in cometary science. When a comet gets close enough to the sun, the solar heat warms its surface. This heat turns the frozen ices like water, carbon monoxide, and carbon dioxide directly into gas. This process is called outgassing. This gas doesn't just seep away, it bursted out from cracks and vents on the comet's surface, creating powerful jets. This is where the rocket part comes in. Based on one of the most fundamental laws of physics, Newton's third law, every action has an equal and opposite reaction. The action: the comet shoots out jets of gas in one direction. The reaction: the comet itself is pushed in the opposite direction. This push is tiny, but it's constant. Over weeks and months, this gentle, continuous push measurably changes the comet's path. It's a force other than gravity acting on the comet. Astronomers have a name for it: non-gravitational acceleration. We are very good at predicting how objects should move based on gravity alone. We can calculate the pull of the Sun, Jupiter, and all the other planets to incredible precision. When a comet's path deviates from this purely gravitational map, we know its rocket engines are firing. For almost every active comet we've ever studied, we see this effect. We extend it. The problem with 3I Atlas. This brings us to the central contradiction of 3I Atlas. This comet is extremely active. In August, measurements showed that Atlas was blasting out an enormous amount of gas. Specifically, it was losing 129 kilograms of carbon dioxide every single second. This is not a small leak. This is a powerful continuous explosion of gas like a massive industrial vent. This level of outgassing must be producing a powerful rocket-like force. Based on everything we know, this force should be pushing the comet and altering its orbit in a way we can easily measure. But when astronomers looked at the comet's path, they found something deeply strange: nothing. The orbit of 3I Atlas was pristine. It was moving exactly as predicted by gravity and gravity alone. All the rocket thrust that should have been there was completely missing. The comet's rocket engines were visibly firing, but the ship itself wasn't moving any differently. This is a massive problem. The observations are in direct conflict. We see the gas, but we don't see the push. Where did the non-gravitational acceleration go? This mystery left scientists with two possible explanations, both of which were very difficult to accept. Explanation 1: the comet is too big. The first possibility is that the force is there, but the comet is just too massive to be moved by it. This is a simple concept of inertia. It is much easier to push a tennis ball than a bowling ball. It is nearly impossible for a person to push a cruise ship. The cruise ship has too much mass or inertia. In this scenario, the 129 kilograms of gas per second is creating a push, but the nucleus of 3I Atlas is so gigantic, so incredibly heavy, that this push is like a single fly trying to move a skyscraper. The force is technically there, but the resulting acceleration is so tiny that it gets lost in the noise. It's too small for our instruments to even detect. For this to be true, 3I Atlas would have to be a true monster. Estimates suggest its solid core or nucleus would need to be 5 to 6 kilometers wide, or perhaps even larger. This would give it a mass measured in the tens of billions of tons. The uncomfortable part. This explanation is uncomfortable because objects of this size are not just comets. They are planetesimals, the original giant building blocks of planets. These massive bodies usually live in very stable, very distant orbits in the cold, dark outer edges of the solar system, like the Oort cloud. How did such a colossal object get kicked from its stable home and sent falling toward the sun? It would imply a very violent and rare gravitational event took place deep in interstellar space long ago. Explanation 2: perfect impossible symmetry. The second possibility is even stranger. This theory suggests that the rocket push is happening, but it's perfectly cancelling itself out. Imagine a small boat with 2 rocket engines. If you only fire the engine on the back, the boat moves forward. But what if you fire an engine on the back and an identical engine on the front at the exact same time with the exact same power? The two forces would balance and the boat wouldn't move at all. This explanation suggests the same thing is happening on 3I Atlas. For every jet of gas pushing it north, another jet is pushing south with the exact same force. All of its 129 kilograms per second of outgassing is perfectly symmetrically balanced. The uncomfortable part. This is considered almost statistically impossible. Comets are not engineered spacecraft. They are lumpy, irregular, potato-shaped objects. They spin and tumble unevenly. The jets of gas are just random cracks and weak spots on the surface. For all these random jets on a lumpy, tumbling rock to perfectly cancel each other out all day, every day is beyond coincidence. It would be like flipping a coin 1,000 times and having it land on heads every single time. No scientist would bet on this. The clue: a heavy metal. So which is it, a giant nucleus or a 1 in a trillion cosmic coincidence? The recent discovery of nickel in the comet's atmosphere provides a very strong clue. Nickel is a metal. Metals are heavy and dense. You don't typically find pure gassy nickel in a normal dirty snowball comet, which is mostly light ice and dust. The presence of this heavy element dramatically strengthens explanation 1: the comet is just too big. The nickel suggests that 3I Atlas is not a fluffy ball of ice. It suggests this object is dense. It may have a solid, heavy core, possibly rich in rock and metals. This would make it even heavier than a normal icy comet of the same size. This connects all the pieces of the puzzle. The comet is a rocket, but it's a rocket engine strapped to a mountain. The force from the carbon dioxide gas is completely overwhelmed by the immense mass and density of the nucleus. The mystery of the missing acceleration is likely solved. The acceleration isn't missing, it's just fighting against an object so massive that it cannot make a difference. This tells us that 3I Atlas is not a normal comet at all, but a new and strange type of object. A massive, dense, ancient relic from the birth of our solar system disguised as a common comet. To truly understand the scientific community's cautious and some might argue dismissive approach to 3I Atlas, we must first rewind to the year 2017. Before 3i Atlas presented its own set of profound puzzles, our solar system was visited by another object that shattered all our expectations. This object was 1i 2017, U1, better known as Oumuamua, a Hawaiian name meaning scout or messenger from here. It was the very first object ever detected passing through our solar system that was confirmed to have originated from another star. This discovery was a monumental event in astronomy. For centuries we had only theorized about such visitors. Now we had one in our own backyard, a physical piece of another solar system that we could study. But as scientists scrambled to observe it, a difficult task as it was already heading away from us. When it was found, they realized Oumuamua was not behaving like anything they had ever seen. The data that came back was not just surprising, it was deeply anomalous. The first puzzle was its shape. By observing how its brightness changed as it tumbled through space, astronomers deduced that Oumuamua was extraordinarily elongated. The leading models suggested it was perhaps 10 times as long as it was wide, shaped like a cigar. Other interpretations of the same light curve data suggested an even stranger form, a very thin, flat disk or pancake shape. Either way, this was not the potato-like or roughly spherical shape we expect from asteroids, nor did it look like a typical comet. Nature does not easily produce objects with such extreme proportions. The second and more significant anomaly was its motion. Like any object, Oumuamua accelerated as it approached the Sun due to gravity looped around it and began to speed away. But as astronomers tracked its exit, they found a critical discrepancy. The object was accelerating faster than gravity alone could explain. This is known as non-gravitational acceleration. In our solar system, we have a perfectly good explanation for this phenomenon in comets. As a comet gets near the Sun, its ices like water carbon dioxide or carbon monoxide heat up and turn directly into gas. This process called sublimation creates a visible cloud, a coma and tail. This outgassing acts like a set of tiny rocket thrusters pushing the comet and causing the exact kind of non-gravitational acceleration Oumuamua was displaying. Here was the problem: astronomers pointed the most powerful telescopes on Earth and in space at Oumuamua, and they could not find any coma. There was no tail, there was no measurable sign of gas or dust. It appeared to be an inert, dry rock or piece of metal. This created a paradox that conventional science could not easily solve. Oumuamua was being pushed by an invisible force. It had the acceleration of a comet, but no coma. Now let us place this 2017 event alongside the 2024 arrival of 3i Atlas. The two objects present a perfect, almost poetic opposition. Oumuamua showed no visible coma, no outgassing, but did display strong non-gravitational acceleration. 3 Atlas shows a colossal coma, massive, powerful outgassing, but displays no detectable non-gravitational acceleration. Oumuamua was an engine with no exhaust. 3i Atlas is a colossal exhaust with no engine. Both objects defy the standard cometry model, just in opposite ways. The standard explanation that outgassing causes acceleration is challenged by both visitors. Into this perplexing Oumuamua mystery stepped Avi Loeb, a professor and former chair of the astronomy department at Harvard University. Loeb is not a fringe figure. He is a mainstream, highly respected theoretical astrophysicist. He looked at the anomalies, the extreme shape, the lack of a coma, and the non-gravitational acceleration, and proposed a hypothesis that was as elegant as it was controversial. He argued that we should take the data at face value. What do we know of that can be pushed by the sun's light, requires no outgassing, and would likely be very thin and flat? The answer he suggested was a light sail. A light sail is a theoretical form of spacecraft propulsion that uses the pressure from photons, particles of light bouncing off a large, thin reflective surface to generate thrust. Humans are already experimenting with this technology. Loeb was not necessarily claiming Oumuamua was a functioning, crude alien ship. He simply proposed that its properties were consistent with a piece of technology, perhaps a defunct probe, discarded sail, or even a deliberate message in a bottle. The object's acceleration, he calculated, was perfectly consistent with it being a thin sail, just a fraction of a millimeter thick, being pushed by the pressure of sunlight. The reaction from the broader scientific community was not just skeptical, it was immediate, deeply negative, and often hostile. The idea was quickly labelled as sensationalism, speculation, and a betrayal of the scientific method. There was a palpable discomfort and anger that a serious scientist would publicly engage with a hypothesis that even hinted at an artificial alien origin. Instead of calmly evaluating the light sail hypothesis as one possibility among many, the community rushed to find any alternative natural explanation, no matter how convoluted. Theories were proposed that Oumuamua was a hydrogen iceberg, a type of object never before seen, and which many physicists argue cannot even form or survive a trip through interstellar space. Others suggested it was the dust bunny, a highly porous, low-density aggregate, or a nitrogen iceberg chipped off a Pluto-like planet in another star system. The problem was that all of these natural explanations required inventing a brand new class of astronomical object, one for which we had no other evidence, just to avoid the implications of the technology-based hypothesis. This brings us to the core reflective question: did the professional and social backlash to the Oumuamua debate create a chilling effect that has directly influenced the study of Three-Eye Atlas? The evidence strongly suggests the answer is yes. The Oumuamua saga was messy, public, and damaging to reputations. The lesson many in the astronomical community took away from it was not, we should be more open to anomalies, but rather do not, under any circumstances, be the person who speculates about anything alien, or you'll be branded as a crank. This institutional fear of being sensational has cast a long shadow over the Three-Eye Atlas investigation. When Three-Eye Atlas arrived, presenting its own impossible physics, a massive coma with zero acceleration, the scientific community was primed to be overly cautious. No agency, and certainly no individual scientist, wanted to be the next Avivi Loeb. No one wanted to be the source of headlines claiming aliens or megastructures. As a result, the default response to Three-Eye Atlas has been to choose the safest possible presentation of the data. The dominant explanation put forth is that the object's massive outgassing must be perfectly absolutely symmetrical. That is, the jets of gas firing from its nucleus must be so precisely balanced on all sides that their net effect on its momentum is zero. While mathematically possible, this explanation is itself extraordinarily improbable. It requires a near-perfect arrangement of vents on a spinning irregular nucleus. It is a just-so story, an explanation of convenience that calms the nerves but ignores the sheer weirdness of the observation. The fear of being wrong has become greater than the curiosity to explore what might be right. The scientific community's reaction to Oumuamua was a failure of imagination. It revealed a deep-seated bias for consensus over curiosity. This precedent, this missed lesson, has now led to an overcorrection. Faced with the profound mystery of Three-Eye Atlas, the establishment has chosen not to see a puzzle demanding a new solution, but a problem to be contained with the safest, most conservative, and least sensational explanation possible, even if that explanation strains credulity. The fear of being labelled sensational has led to a scientific approach that is perhaps not nearly sensational enough for the object we are witnessing. The journey of this object through our solar system is not just a scientific curiosity, it is a profound statistical puzzle. Its path is defined by numbers that are hard to explain away as mere chance. The two most important numbers are its velocity, its speed and direction, and its eccentricity, the shape of its orbit. First, the numbers that prove it is not from around here. The object was measured moving at an incredible 58 kilometers per second relative to our Sun. To understand how fast this is, the Earth moves at about 30 kilometers per second. This speed is far beyond the escape velocity of our solar system. Nothing naturally belonging to our Sun can travel that fast on its own. This speed is the clearest evidence we have that this object is a visitor from interstellar space, the void between the stars. This conclusion is locked in by its orbital eccentricity, which was calculated to be 6.2. In astronomy, eccentricity is a number that describes the shape of an orbit. A perfect circle is 0. A typical planet's orbit, like Earth's, is slightly stretched, perhaps 0.016. A long stretched out comet orbit might be 0.9. The absolute limit for any object that is bound to our Sun, meaning it will eventually return, is 1.0. This object's eccentricity was 6.2. This number isn't just slightly over the limit, it is wildly hyperbolic. It means the object is on a path that is barely being bent by our Sun's gravity. It is slicing through our solar system at high speed, completely unbound, destined to fly back out into deep space, never to return. If its speed confirmed it was an outsider, its path revealed just how strange this visitor was. The object's orbit was unusually flat relative to the rest of the solar system. It travelled on a path inclined only 5 degrees from the ecliptic plane. The ecliptic is the flat disc-like racetrack on which all the planets from Mercury to Neptune orbit the Sun. Most things in our solar system move along this plane. This object, however, was driving on that racetrack, but in the wrong direction. While it stayed almost perfectly on the same flat plane as the planets, it was moving in a retrograde motion. It was flying against the flow of all the planets. This is exceptionally strange. Our solar system formed from a giant spinning disk of gas and dust. Everything in that original disk spins in the same direction prograde. A retrograde object suggests it had a very chaotic past or was captured from somewhere else. But for an interstellar object to arrive and be almost perfectly aligned with our solar system's plane but be moving backward is a cosmic coincidence of the highest order. This leads to the statistical impossibility of its path. When astronomers calculated the odds of this specific orbit, the numbers were shocking. The probability of an interstellar object entering our system having this low inclination being retrograde and happening to pass close enough to Venus, Mars and Jupiter to be observed as it was is vanishingly small. The calculated chance was approximately 0.05%. To put this in perspective, that is a 1 in 20,000 chance. It is, as some have called it, a lottery ticket orbit. When something that unlikely happens, scientists have two choices: accept that we just witnessed a 1 in a million fluke, or ask if perhaps the orbit wasn't a random chance. What if the path was in some way deliberate? This is where the discussion moves from astronomy to intense controversial debate. Professor Avi Loeb of Harvard University, known for his willingness to explore unconventional ideas, has looked at these anomalies and proposed an alternative. He draws a fascinating comparison to a different object, the comet 3I Atlas. Comet 3I Atlas was a normal comet. When it got close to the Sun, the ice and dust it was made of began to heat up and vaporize. This vaporization outgassing created a visible tail. Crucially, this outgassing also acted like a tiny, unpredictable rocket engine, pushing the comet slightly off its gravitationally predicted path. This non-gravitational acceleration is normal for comets. 3I Atlas eventually disintegrated under the Sun's heat, a typical fate for such an icy body. Now look back at this mysterious object. According to the data, a key mystery was its lack of acceleration. It flew close to the Sun, yet it did not show any signs of outgassing. It did not produce a tail. It did not experience the slight push seen in comets like 3I Atlas. It sailed past the Sun intact and undisturbed, despite a path that should have, if it were an icy comet, caused it to act like one. Loeb connects this lack of cometary behavior to a radical idea, a controlled push. If this object isn't a natural rock or ice ball, but is instead a piece of technology, its behavior makes a different kind of sense. A thin, rigid structure, perhaps a solar sail designed to be pushed by starlight, would not outgas. It would not disintegrate like 3I Atlas. Its lack of acceleration, meaning the lack of cometary acceleration, is exactly what you would expect from a solid artificial object. Its trajectory, while seeming like a lottery ticket for a natural object, might be perfectly logical for a probe designed to visit multiple targets or use planets for gravitational maneuvers. This hypothesis that the object is artificial is often dismissed as science fiction, but Professor Loeb argues that it is in fact good science. Why? Because it is testable. A scientific hypothesis is only valuable if it makes specific predictions. The alien tech hypothesis does this. It predicts that if we find more objects like this one, they too will lack the chemical signatures of a comet or asteroid. It predicts that the object should be thin and have a large surface area to mass ratio to sail on light. It predicts that if we could have gotten a closer look, we would not have seen a tumbling potato-shaped rock, but perhaps a structured manufactured object. If, for example, we later found a similar object and discovered it was clearly outgassing or was a solid chunk of nickel-iron, Loeb's hypothesis for this object would be weakened. If we find more objects like it that also defy natural explanation, his hypothesis is strengthened. The point is not whether he's right or wrong. The point is that he has offered a theory that can be tested against future evidence. This is what separates science from mere speculation. This controversy has been fueled by an element that is not astronomical but human, the silence of major space agencies. Data on this object was collected by multiple telescopes, including those operated or funded by NASA. While the mainstream scientific consensus has defaulted to the unknown natural origin explanation, there has been a notable lack of public detailed explanations from these agencies specifically addressing why the artificial hypothesis is wrong. Avi Loeb and others have pointed this out. Why not publicly release all the analysis showing why the data is incompatible with the solar sail theory? This silence creates suspicion. When the data is unusual, the probability is astronomical, and the alternative theories are testable. Simply ignoring the unconventional hypothesis is not a sufficient scientific response. It creates an information vacuum. Into that vacuum, speculation and doubt will always rush in. The public and even other scientists are left to wonder, are they silent because the idea is too ridiculous to address, or because the data they have doesn't comfortably rule it out? This brings us to one of the most difficult puzzles Oumuamua presented its size. When astronomers pointed the powerful Hubble Space Telescope toward the object, they couldn't get a clear image. It was too small, too far, and moving too fast. All Hubble could do was measure its faint brightness. From that tiny data point, scientists had to work backward. An object's brightness depends on two things: its size and how reflective it is, a quality called albedo. If Oumuamua was very shiny like a comet made of fresh ice, it could be quite small. If it was very dark like a rocky asteroid or a lump of coal, it would have to be much larger to be as bright as it was. This gave scientists a wide range of possibilities. Based on the Hubble data, Oumuamua's length was estimated to be somewhere between 0.32 kilometers and 5.6 kilometers. This wide range, however, created a perfect logical trap, a catch-22, from which the natural explanations could not escape. Here is the paradox. Let's look at both ends of the estimate. The small problem. First, let's assume Oumuamua is on the small side, for example, around 0.5 kilometers long. This seems reasonable. An object of this size would be light enough to be pushed by the mysterious non-gravitational force matching the acceleration we observed. But this solution creates a new unsolvable problem. What was pushing it? The only natural force that could push an object this small is outgassing, just like a comet. As a comet gets near the Sun, its ices turn into gas, shooting out like tiny jets and pushing the comet forward. But if Oumuamua was a 0.5 kilometer wide comet, it would have been incredibly active. It would have been a spectacular sight. The heat of the Sun would have created a massive, brilliant tail of dust and gas, a coma that would have been unmistakably clear to telescopes. We looked with everything we had. There was no gas, there was no dust, there was no tail. So if it's small, it cannot be a comet. What about solar radiation pressure? This is the tiny push that sunlight itself exerts. For a small rocky object, this push is almost zero. It's far too weak to account for the major acceleration Oumuamua displayed. Therefore, if Oumuamua is small, we are left with an object that is accelerating strongly for no reason at all. It breaks the laws of physics. The large problem. Okay, so the small theory doesn't work. Let's go to the other end of the Hubble data. Let's assume Oumuamua is very dark and very large, closer to the 5.6 kilometer estimate. This immediately solves the acceleration problem. An object this massive would only be slightly pushed by the non-gravitational force. Its great mass would mean the push was actually very gentle, perhaps small enough to be caused by a small undetectable amount of outgassing. But this too creates an impossible problem. This time the problem is not one of physics, but of statistics. An object 5.6 kilometers long is not a piece of debris, it is a monster. It is a significant mountain-sized or city-sized chunk of another solar system. Our models of how solar systems form show that for every one large object like this, there must be billions of smaller ones. And getting an object this large ejected from its home star system is incredibly difficult. It would require a massive gravitational event, one that is very rare. If Oumuamua, the very first interstellar object we ever saw, was a 5.6 kilometer giant, it would mean the galaxy is overflowing with these massive objects. It would mean our understanding of planet formation is not just wrong, but catastrophically wrong. Such an object as the first one we find is a black swan, a statistical impossibility that breaks all our models. We should have seen thousands of smaller ones first. This is the catch-22. If Oumuamua is small, we cannot explain its acceleration. If it is large, we cannot explain its existence. Both natural explanations fail. This is where Professor Avi Loeb introduced his formal analysis. He applied a tool from mathematics called Bayesian logic. This is a way of calculating how your belief in a hypothesis should change when you get new evidence. Loeb argued that the scientific community started with a prior belief that was 100% it must be natural and 0% it might be artificial. But he argued the evidence should force us to update that belief. The evidence is the small hypothesis a natural comet fails because it should have had a tail. The large hypothesis a natural asteroid fails because it's a statistical impossibility. But a third hypothesis fits the data perfectly: a solar sail. A solar sail is a piece of technology designed to be pushed by sunlight. It would be very thin light and reflective. It would accelerate powerfully from solar radiation pressure without any tail. It neatly solves the small problem. It also solves the large problem because it is not a 5.6-kilometer rock. It is a lightweight piece of technology, and we have no statistics on alien tech to break. Because the two natural explanations are so poor, Loeb's analysis concluded that the probability of the artificial hypothesis being correct was significant. He estimated it at 30 to 40%. This leads to the final troubling question. The mainstream scientific community, including NASA, aggressively dismissed Loeb's conclusion. They insisted it must be natural. But if they were so confident, why did they not publish their own statistical analysis? Why did they not offer a formal Bayesian argument showing that the Black Swan 5.6-kilometer rock was not a statistical impossibility? Their failure to engage with the size paradox on its own terms is telling. They offered no solution to the catch-22. They simply ignored it, preferring to propose other equally strange natural theories like a nitrogen iceberg, an object no one has ever seen, rather than confront the data that was right in front of them. The fleeting, frustrating encounter with SOHO had left the world on edge. The scientific community was buzzing not with discovery, but with a tense, agitated energy. The public, fed on a diet of blurry images and official evasions, had turned skeptical. Every no comment was treated as a yes. Every silent, unmoving data stream was interpreted as a hidden message. The comet was no longer just an astronomical object, it was a mirror reflecting humanity's deepest suspicions about the very institutions it relied on. Into this atmosphere of distrust, the comet continued its journey. The next major milestone was October 13th, 2025. On this day, C24V3 would make its closest approach to the red planet. The geometry was once again challenging. The comet would pass Mars at a distance of 0.19 astronomical units. This is roughly 19% of the distance from the Earth to the Sun, a vast distance in human terms translating to over 28 million kilometers or 17 million miles. While it was not a near miss, it was the closest any of our active robotic explorers would get to the object. All eyes metaphorically turned to Mars. The planet was host to a small fleet of orbiters and rovers from multiple nations. This was the real chance. Not a glancing blow from a solar observatory, but a dedicated look from sophisticated science instruments. The hope was that the Martian assets could succeed where the SOHO pass had failed. The public and the press were hungry for a clear picture, for a definitive answer. What they received, however, was a masterclass in ambiguity. The TGO glimpse. The first and only official confirmation of an observation came from the European Space Agency ESA. Their ExoMars Trace Gas Orbiter TGO, a sophisticated satellite designed to sniff the Martian atmosphere for faint chemical traces, had attempted to image the comet. The challenges were immense. TGO's cameras are built to look down at a bright sunlit planet, not out into the dark void at a faint fuzzy object. The comet was moving, TGO was moving, and Mars was moving. The ESA engineers performed an impressive feat of orbital gymnastics just to get the orbiter pointed in the right direction. On October 14th, ESA released the results. The word they used was difficult. The images were faint, blurry, and heavily processed. They showed a small, indistinct smudge of light. The agency's press release was cautious and technical. They confirmed that the object was active. They could identify a coma, the fuzzy halo of gas and dust boiling off the comet's surface. This confirmed that C224V3 was, at least in its behavior, a comet. But the one thing everyone wanted to see remained a mystery. The nucleus, the core problem, as it was being called, was not resolved. It was impossible to tell if the bright smudge at the center of the coma was a single object, a cluster of objects, or something else entirely. The image was just too blurry, the distance too great. It was a scientific confirmation, but an emotional disappointment. We had proof. It was a comet, but we still had no idea what it was. The TGO image was just clear enough to confirm something was there, but just blurry enough to let the imagination run wild. The ghost on the ground. The real storm, however, was not brewing around the data we got, but the data we didn't. The silence from NASA was becoming the central part of the story. The primary rumour focused on the Perseverance rover, operating in Jezero Crater. Perseverance was NASA's most advanced rover on the surface. It was equipped with a suite of high-definition cameras, including the powerful Mastcam Z. The public's question was simple. Did you point the camera up? It was a logical request. Yes. From the surface of Mars, the comet would have been visible in the sky. It might have been faint, perhaps lost in the twilight glow of the dusty Martian atmosphere, but it should have been there. An image of the comet from the surface of another world would be historic. NASA, however, said nothing. Online forums and social media channels lit up with speculation. Analysts argued that the rover's cameras were more than capable of capturing such an image. If the comet was as bright as some models predicted, it should have been an easy target. The unconfirmed status of this observation became a wound that the agency kept poking. The silence was deafening. Why wouldn't they take the picture? It was a simple low-risk, high-reward observation. This is where the core problem took root. The conspiracy theories wrote themselves. A simple "no, the observation wasn't possible" would have been met with grumbling but eventual acceptance. A "yes, we looked and saw nothing" would have been disappointing, but it would have been data. The silence, the refusal to confirm or deny, was seen as an admission. The only logical reason for NASA to remain silent, the argument went, was because Perseverance did take a picture. And that picture must have shown something they did not want the public to see. Something that was not just a fuzzy dot. Something that confirmed the visitor hypothesis. The GOES rumour and the problem of silence. The second ghost observation was even stranger, highlighting the paranoia of the moment. A rumour began circulating that the GOES 9 satellite had also captured an image of the comet. GOES 19, operated by NOAA, the National Oceanic and Atmospheric Administration, is an advanced geostationary weather satellite. Its primary job is to watch Earth's weather patterns and provide early warnings for hurricanes and tornadoes. The idea that it would be used for deep space astronomy was on its face absurd, but the prompt had mentioned a strange rumour about an observation when the comet was behind the Sun, referring to the Soho Pass. This new rumour seemed to be an echo of that. The logic was convoluted if the comet was anomalous. Perhaps it was affecting the solar wind, and perhaps the space weather instruments on GOES 19 picked up this disturbance. Like the Perseverance rumour, NOAA's official response was nothing, unconfirmed. This problem of silence was the key. As the user's notes rightly identified, a simple yes or no would have ended the speculation. No, GOES 19 did not observe the comet. That is not what the satellite does. This would have stopped the rumour cold. No, Perseverance did not image the comet. Its primary mission schedule in Jezero Crater took priority. This would have angered some, but it would have been an answer. The silence allowed ambiguity to fester and grow into full-blown conspiracy. The lack of a no was interpreted as a "we can't say no, so we're saying nothing." This ambiguity was the perfect fertilizer. It suggested that the truth was so fragile, so world-changing, that it had to be protected by a wall of institutional silence. The public felt it was being treated like a child. The refusal to deny the rumours gave them a power and a legitimacy they never would have earned on their own. As October 2025 came to a close, the comet was moving away from Mars, heading back into the cold, dark void. It had given us one blurry photo and a mountain of questions, but the comet itself was no longer the main story. The story was the silence. The agencies, by trying to control the narrative, had lost it completely. They had turned a scientific mystery into a human one. If we accept the premise that we are part of a pedagogical exercise, a lesson, or perhaps a test designed by a visitor, then we must look for the textbook. We must find the evidence that they have left for us to find. That evidence, according to a stunning paper posted on the scientific server known as Arxiv, might be the Object 3I Atlas. This paper, authored by a team of astrophysicists including Loeb Hibbard and others, is not a light piece of reading. It is a deep mathematical analysis of the object's path through our solar system. The authors of the paper are not newcomers. They are serious scientists who have spent their careers studying the sky. And what they found is deeply troubling, or perhaps deeply exciting. The core of their analysis is not about what 3I Atlas is made of ice rock or metal, but about where it has been and where it is going. Its path, its trajectory is the entire mystery. What the paper highlights first is a coincidence so extreme that it borders on the impossible. The calculated probability of a natural object following this specific path by chance alone is estimated to be around 0.05%. That is not zero, but it is small enough to make any scientist stop and ask, why? What is this incredibly rare event? It is a series of planetary flybys, or close passes. The object's path brought it near Venus, then near Mars, and then sent it swinging by the gravitational pull of the giant Jupiter. For a natural object, this is like a billiard ball navigating a complex table and lightly touching 3 specific targets in a row without any outside help. It's possible, yes, but it's extraordinarily unlikely. But this billiard shot is not even the strangest part. The true anomaly, the detail that forms the core of the visitor hypothesis, is about timing. The paper points out that 3I Atlas reached its perihelion, its closest point to our Sun, on October the 29th, 2025. This is the moment the object is moving fastest, pulled in by the sun's immense gravity. It is the single most critical moment in its entire journey through our solar system. And at that exact moment, something else happened. A solar conjunction. A solar conjunction is simple to understand. It is when, from our viewpoint here on Earth, the object 3i Atlas lines up perfectly with the sun. The object moves behind the sun. This means that on October 29th, at the precise moment 3i Atlas was at its closest, fastest, and most important point, it was completely invisible to us. All of our telescopes, from the largest observatories to the Hubble and Webb space telescopes, were blinded. You cannot look at an object that is hiding directly behind the sun. The sun's own light makes it impossible. If you are a comet, this timing is just bad luck for astronomers. If you are a visitor planning a maneuver, this timing is perfect. This brings us to the most startling hypothesis in the paper, the reverse Oberth maneuver. In space travel, there is a famous trick called the Oberth maneuver. It is the most efficient way to gain speed. The concept is simple. If you are going to fire your engines to speed up, you should do it when you are already moving at your fastest at your closest point to a massive body like the sun. Doing this gives you a massive boost in speed, far more than you would get if you fired your engines in deep space. The paper suggests the opposite. What if the visitors did not want to speed up and leave? What if they wanted to slow down and stay? If you want to slam on the brakes in space, the most efficient way to do it is the reverse Oberth maneuver. You fire your engines against your direction of travel, but you do it at the moment of your highest speed at perihelion, the closest point to the sun. A braking burn at this exact moment would slow the object down more dramatically than a burn at any other time. It would be enough perhaps to change its path from a flyby, leaving the solar system, to a captured orbit staying here with us. Now let us put all the pieces together. The object follows a path of impossible flybys, Venus, Mars, Jupiter, to get to the sun. It arrives at its closest, fastest point perihelion on October 29th. This is the perfect time to perform a reverse Oberth maneuver to hit the brakes and enter our solar system. And coincidentally, this exact date, October 29th, is when the object is perfectly hidden from Earth behind the sun, the solar conjunction. If you wanted to enter our solar system, park your ship in orbit, and do it without anyone seeing the massive engine burn required for the maneuver, this is exactly how you would plan it. You would use the sun as a giant curtain, performing your biggest move while you are hidden in its blind spot. This is the visitor's plan that the paper outlines. It is a plan that is brilliant, stealthy, and terrifyingly intelligent. But the most important part of the paper, the element that makes this true science, and not just science fiction, is the final section, testability. The authors Loeb and Hibbard do not just present this wild idea and walk away. They provide a clear, simple way to prove their hypothesis wrong. This is the final exam of the pedagogical exercise. The prediction is this. If 3i Atlas is just a dumb rock, a natural comet, then even after it passes behind the sun, its path will be predictable. It will follow the laws of gravity just as it always has. It will emerge from the sun's glare, and we will find it exactly where we expect it to be. But if it is an artificial visitor ship, and if it did perform a braking maneuver, the reverse Oberth maneuver, while it was hidden, then its path will have changed. It will have slowed down. When it emerges from behind the sun, it will not be where we expect it. It will be on a new, different orbit, an orbit that proves it is not subject to gravity alone. The paper gives us a date for this test. The object will begin to emerge from the sun's glare in mid-November 25. By late November or early December 25, our telescopes will be able to get a clear view. We will point our telescopes to where the comet should be. If we find it there, the hypothesis is wrong. It was all just a wild statistical miracle. If we look and it's not there, or if we find it on a new, slower path, then everything changes. The test will be complete, the lesson will have been delivered. We are now in the final weeks of the exercise. We are waiting for the object to come out from behind the curtain. We are waiting to see if we have been observing a rock, or if a visitor has just very quietly and very skillfully parked on our doorstep. The moment a significant discovery is made, two separate stories are born. The first is the story the scientists tell each other. The second is the story they or their institutions decide to tell the public. With this comet, the gap between these two stories is not just a crack, it's a canyon. This gap is best seen in the specific words chosen. When the official NASA press release describes the object as an interesting comet, it is using language that is precise, deliberate, and above all safe. Interesting is a word of mild curiosity. It invites the public to look up and be curious, but not to be alarmed. It frames the event as a cool science moment, something for textbooks and documentaries. It implies control, It suggests that this is just another data point in our grand orderly understanding of the universe. The scientific paper, however, tells a completely different story. This is the conversation happening behind the curtain. The words used here are not interesting. The words are unprecedented and not predicted by our models. In the world of science, these phrases are explosive. Unprecedented means we have no previous map for this. Not predicted by our models is an even more profound statement of vulnerability. It means the rulebook that scientists have spent decades writing, testing, and trusting has just been proven incomplete or perhaps wrong. It is the scientific equivalent of an emission of shock. One word, interesting, is designed to calm and reassure. The other phrases, unprecedented and unpredictable, are admissions of profound uncertainty and surprise. The strategy of omission. To be clear, NASA is not lying. The comet is interesting, but this is a lie by omission. They are presenting a conclusion while hiding the entire argument. It's like a doctor looking at a truly bizarre, never-before-seen X-ray and telling the patient, that's an interesting freckle. The statement is technically true, but it deliberately omits the vital context that it is interesting, precisely because it is shocking and unexplainable. This strategy is known as sanitization. The raw data, the messy, confusing, and slightly terrifying reality is keened before it's presented to the public. The fear, the uncertainty, and the professional shock of the scientists are filtered out. What remains is a sterile, simplified, and non-threatening version of the truth. Why do this? The official motive is always to manage the message, but what this really means is managing the public. Why the caution? This intense caution from official agencies stems from three core fears. The first and most obvious is the fear of public panic. There is a deep-seated belief within many institutions that the public is a fragile entity, one piece of bad news away from War of the Worlds-style mass hysteria. They believe their primary job in a crisis is not just to relay information, but to keep people calm. The problem is that keeping calm often translates to withholding the full truth. They fear that if they admitted, "We have seen something that our models cannot explain," the public would interpret this as we are all doomed. The second is the fear of sensationalism. This is a battle with the media. Agency public relations officers know that if they use a word like unprecedented, the headlines will not be nuanced. They will be "Mystery Comet defies science, could it be a threat?" or "NASA baffled by a rogue object." To prevent this kind of clickbait, they preemptively starve the media of any dramatic language. They use the most boring, neutral words possible. Interesting is the perfect defense against sensationalism. It's too boring to twist. The third fear is perhaps the most dangerous, the fear of admitting we don't know. In our culture, we expect our scientific institutions to be all-knowing. We fund them to have the answers. For an agency like NASA to stand at a podium and say, "This object is behaving in a way that none of our theories can account for," it would be an admission of fallibility. It might be interpreted as incompetence. In science, saying "I don't know" is the exciting first step toward a new discovery. But in public relations, it's seen as a failure of authority. They are afraid of losing public trust, so they project an image of calm even when their own data is telling them to be anything but calm. The rumour mill and the sci-fi. This strategy of sanitizing the truth has a disastrous side effect. It creates an information vacuum, and a vacuum will always be filled. When the public senses a mismatch when they read the calm, interesting press release but then hear whispers from leaked papers about unprecedented behaviour, they don't simply trust the official source. They assume the official source is hiding something. This is where the rumours about the International Asteroid Warning Network IAWN are born. The IAWN is the planet's official tripwire. Its job is to coordinate a global response if a serious threat is detected. The question, was IAWN activated, is a terrifying one, and the fact that there is no clear public yes or no is a catastrophic communication failure. The silence from official channels does not calm people. It forces them to seek information from unofficial channels, from forums, from social media, from whistleblowers. The speculation that fills this void is almost always worse than the truth. By trying to prevent panic, the sanitized communication strategy has ironically created the perfect breeding ground for it. A lack of reliable information is the very definition of uncertainty, and uncertainty is the engine of fear. The public is left guessing whether the interesting comet is a scientific curiosity or the subject of a secret high-level emergency meeting. This gap destroys the one thing an agency needs in a crisis: trust. When the full truth eventually comes out, and it always does, the public will remember being misled. They will remember that interesting was a code word for we were shocked. And the next time a real crisis happens, the next time an agency says don't panic, the public will have every right to ask, what are you not telling us this time? We have now reached the single most critical moment in the story of 3I Atlas. As of today, October 29th, 25, the object is at perihelion. This is the point in its orbit where it is closest to the Sun, the moment of maximum danger and maximum stress. It is skimming the Sun at an incredible velocity, during a blast of heat and radiation that is difficult to comprehend. This is the ultimate test. If 3I Atlas is what most conventional models assume a comet made of ice and dust, this intense solar encounter is likely its end. We would expect it to disintegrate, boiling away into a cloud of gas and debris, never to be seen again as a single object. If, however, it is something more robust, such as a dense rocky asteroid, it might survive the passage scarred but whole. And if it is the object of extraordinary speculation and artificial craft, it would likely be made of materials designed to withstand exactly this kind of trial. The climax of the movie is happening right now. The problem: we are flying blind. The agony of flying blind. From Earth's perspective, 3I Atlas is currently lost in the Sun's overpowering glare. It is impossible for any ground-based telescope or even orbital telescopes like Hubble and the James Webb Space Telescope to see it. The Sun itself is a blinding wall of light and the object is right in front of it. This is the great frustration for astronomers worldwide. We know the most important event is happening, but we have no way to watch it. We have spent months tracking this object, debating its nature and anticipating this very moment. Now all we can do is wait. However, humanity is not entirely blind in the inner solar system. We have robotic sentinels in the Sun's neighbourhood, probes built specifically to study our star. In theory, they are in the right place at the right time. The key question is, are they looking? The Potemka is include NASA's Parker Solar Pool. This is humanity's most daring solar explorer. Its mission is to literally touch the Sun by flying directly through its outer atmosphere, the corona. Parker is armed with a powerful suite of instruments including imagers designed to look at the solar wind. It is built to survive extreme heat and is arguably the best placed asset to get a glimpse of 3I Atlas as it flies past. ESA's solar orbiter. The European Space Agency's probe works in partnership with Parker. It has a different orbit one that will eventually allow it to see the Sun's poles. It too has powerful imagers like SOLO-HI that are designed to spot faint structures in the solar wind. A passing object like 3I Atlas is exactly the kind of thing it could detect. NOAA's GOES 19. This is a bit different. It's a weather satellite primarily focused on Earth. However, it also carries sophisticated instruments like a solar ultraviolet imager that constantly monitor the Sun for flares and space weather events. Herein lies the problem. We have received no confirmation that any of these agencies, NASA, ESA or NOAA, are actively tasking their spacecraft to look for 3I Atlas. These are complex multi-billion-dollar missions with very specific scientific goals. Their observation schedules are often planned months or even years in advance. Their primary goal is to study the Sun, not to hunt for an interstellar object that just happens to be passing by. It is entirely possible that they are simply pointed in the wrong direction. Or their instruments might not be optimized to see an object like this. They are looking for gas clouds and magnetic fields, not necessarily a small solid point of light. The silence from the mission teams is deafening. It's a potentially historic missed opportunity. It's also possible they are collecting data and we just don't know it yet, as the data must be downloaded, processed and analysed. For now, we remain in the dark. The waiting game. This period of blindness will not last forever. 3I Atlas is moving incredibly fast. As it swings around the Sun, its orbit will begin to carry it away from the Sun's position in our sky. Astronomers are eagerly awaiting the next observation window, which will open in the first weeks of November. As the object moves further from the Sun, it will eventually reappear, emerging from the bright twilight. It will likely become visible in the pre-dawn sky, a faint ghost rising just before the Sun. Observatories across the world are already preparing. In Chile, Hawaii and Arizona, telescopes will be pointed at the precise patch of sky where 3I Atlas is predicted to emerge. The first images captured in early November will be, without exaggeration, some of the most anticipated in modern astronomy. What will we see? Case 1. Nothing. If the object was a standard comet, it may have completely disintegrated. We will see nothing but empty space. This would be the conventional answer. Case 2, a faint fuzzy cloud. It may have broken apart, leaving a diffuse trail of dust and gas. This would also support a cometary origin. Case 3, a single solid point of light. If it reappears as a sharp, singular object, it means it survived. This would be the most exciting outcome. It would prove the object is dense solid and not made of volatile ices. The verdict on the predictions. The data we gather in early November will just be the beginning. This is when the real test begins, specifically for the bold predictions made by theorists like Avi Loeb. Loeb and others have made testable hypotheses. They suggested 3I Atlas was not a comet. Therefore, they predict it will survive perihelion. They predict it will not look like a fuzzy, gassy comet on the other side. To get the final answer, we will need time. We will need more than just one picture. Over the course of late November and early December, we will gather enough data to know for sure. Astronomers will perform astrometry. We will measure its exact position to see if its path has changed. Did solar radiation pressure push it more than expected? This could tell us about its shape and density. Photometry. We will measure its brightness. Is it stable or is it tumbling? Did it get darker or brighter after its fiery pass? Spectroscopy. This is the most important. We will split its faint light into a rainbow to see what it is made of. Will we see the signature of rock metal? Or will we see the gassy emissions of a typical comet? By the first week of December, we will have the data. The scientific community will be able to compare the before and after states of 3I Atlas. The debate will in all likelihood be settled. We will finally have our answer. As for other remote possibilities, there has been speculation about missions like Europa the Clipper heading to Jupiter or Hera heading to an asteroid. Could they pass through the dust cloud left by 3I Atlas? This is extremely unlikely. Space is unimaginably vast. The chances of such a flyby happening by pure coincidence are almost zero. These are not confirmed opportunities, but rather distant hopes. Our focus remains firmly on the coming weeks. The suspense is at its peak. We are blind at the most important moment, but the darkness is about to lift. The profound, crushing substance of the cosmos weighs on the human spirit. We have spent generations listening, straining our ears for a single whisper in the static, a single note that is not our own. This quest defines our loneliness. It is a dual-edged sword of emotion. On one side, there is a deep, almost spiritual hope, the hope that we are not a cosmic mistake, a brief accidental flicker of consciousness in an empty universe. To find another intelligence would be to find family. It would validate our own existence, proving that life and thought are not flukes but perhaps fundamental parts of the cosmic equation. It would mean that across the unimaginable gulfs of space, someone else is also looking up at their stars wondering if they are alone. This hope drives us to build vast telescopes and send messages in bottles to the stars. But this hope walks hand in hand with a primal fear. What if the answer to our call is not friendly? Our own human history is a bloody tapestry of conflict, colonization, and misunderstanding between cultures that were in the grand scheme almost identical. What would happen if we encountered a being whose biology, morality, and logic were truly fundamentally alien? The fear is not just of invasion, but of irrelevance. We could be the ants on the sidewalk, noticed only when we get in the way of a force we cannot possibly comprehend. This anxiety is the shadow of our hope. An object like 3I Atlas passing through our home becomes the focal point for this ancient tension. It is a knock on the door in the middle of the night. We are terrified of who might be there, yet we are desperate to answer it. This encounter, whether it is with an artifact or a simple strange rock, forces upon us a necessary dose of science as humility. As a species, we have grown confident, perhaps even arrogant. We have split the atom, mapped our own genome, and stared back to the dawn of time. We build complex models of the universe and we pat ourselves on the back when our observations fit neatly into our equations. We have begun to believe our own press. But 3I Atlas challenges that confidence. It is an anomaly, an asterisk, next to our tidy theories. Its unusual properties, its unexpected path, or its strange behavior force our brightest minds to admit three of the most important words in scientific progress: we don't know. This object, whatever its origin, serves as a powerful corrective. It reminds us that our understanding of the universe is not a vast, complete library, but rather a single-page pamphlet. It shows us that nature and perhaps other natures are more imaginative than we are. We are not the masters of the cosmos. We are toddlers just learning to walk, and 3I Atlas is a stark reminder that the adult world is far more complex and strange than we have allowed ourselves to believe. We have only just begun our journey. This humility slams us directly into the problem of proof. In science, we live by a mantra: extraordinary claims require extraordinary evidence. But when dealing with the possibility of an extraterrestrial artifact, how high is that threshold for proof? If 3i Atlas were a perfect metal cube etched with prime numbers, the case would be closed. But reality is rarely so simple. What if the evidence is not a smoking gun, but a series of unsettling probabilities? What if the object's chemical signature is just unlikely for a natural comet? What if its acceleration is probably not caused by outgassing? Science thrives on certainty, but 3i Atlas may only offer ambiguity. We are forced to ask what constitutes artificial. We are looking for things that look like our technology radio signals engine burns metal hulls. But a civilization a million years ahead of us might use technology, indistinguishable from nature or even from magic. Their artifact might be a biological construction or a machine that swims through space-time. This leads to the most unsettling question of all. What happens if the evidence is forever ambiguous? What if we are visited by dozens of such objects, all of them strange, all of them suggestive, but none of them conclusive? We would be trapped in a cosmic limbo, a state of permanent suspicion. We would have to accept that one of the greatest questions humanity has ever asked, are we alone, may not have a simple yes or no answer, but a permanent frustrating maybe. This ambiguity is a form of intellectual torture for a species that craves answers. Ultimately, this is why the object itself almost doesn't matter. What matters is the mirror it holds up to us. The true revelation of 3i Atlas is not what it is, but what it shows us about ourselves. Our reaction to it says more about humanity than the object could ever say about aliens. Look at the spectrum of responses. We see profound skepticism, a near unwillingness to even entertain the artificial hypothesis. This reflects our need for order, our reliance on known laws, and our fear of being fooled. It is the immune system of science protecting the body of knowledge from the virus of wishful thinking. We see immediate breathless belief. This reflects our deep loneliness, our desire for magic, and our cultural saturation with science fiction. We want it to be a ship because we are bored or scared or simply hopeful for a grander story. And we see fear and suspicion. We see whispers of a potential cover-up, the idea that they know the truth but are hiding it from us. This profound cynicism reveals not our thoughts about aliens, but our deep-seated distrust of our own power structures. It shows we believe we are children incapable of handling a truth that would shatter our religion's economies and sense of self. In the end, 3i Atlas is a Rorschach test, a cosmic ink blot. Some of us see a rock, some see a ship, some see a threat, and some see salvation. But in every case, the image we are seeing is just a reflection of our own faces staring back at us from the void. What we are witnessing with 3i Atlas is not just a singular strange event. It is the beginning of a profound shift in our understanding of the universe. This object, whatever its final classification, serves as a catalyst, forcing us to confront a new reality. We are no longer isolated. The space between the stars is not empty. It is a highway, and we are just starting to see the traffic. This is not a lone traveller. The age of interstellar objects is dawning. We must understand that Oumuamua was not a one-time anomaly, 2i Borisov was not a fluke, and 3i Atlas is not the last. Very soon, new tools like the Vera Rubin Observatory will come online. This observatory is a marvel designed to scan the entire visible sky every few nights. It is a data-gathering machine of incredible power. When it begins its work, the discovery of objects like these will not be a rare event happening once every few years. We will begin finding them regularly. We will find dozens, perhaps even hundreds. We are moving from a trickle of information to a flood. We are standing at the very beginning of true interstellar astronomy. This is precisely why the lessons we learn from 3i Atlas are so critical. How we handle this object, the science we do, the questions we ask, and most importantly the way we communicate will become the template for the future. This is a dress rehearsal. If we get this wrong, if we fumble the communication, create confusion and allow suspicion to grow, we will be doomed to repeat these same mistakes when the next object arrives, and the next one might be even stranger. The confusion and lack of clarity surrounding 3i Atlas demonstrate that our current protocols are not ready for this new era. We have a chance to build a better model, but we must act now. The primary failure we are witnessing is one of communication. The perceived silence from official bodies like NASA, while perhaps intended to ensure accuracy, is having the opposite effect. It is backfiring. In the age of instant information, a vacuum of credible data does not create patience, it creates suspicion. When the public is buzzing with legitimate questions about an object that is behaving strangely, and the primary sources of information are quiet, people do not assume the scientists are just being careful. They assume they are being secretive. This silence is dangerous because it directly breeds mistrust. It creates a space where assumptions and conspiracy theories can grow unchallenged. When official voices are absent, unofficial ones become louder. The public is left to connect the dots on their own, often without the necessary context. This damages the long-term trust between the public and the scientific institutions that serve them. When a real critical announcement does need to be made, the public may be less likely to believe it. Silence is not a neutral position. In this context, it is an actively harmful one. So what do we truly need moving forward? The solution is not more secrecy, it is radical transparency, even when it is uncomfortable. First, we need transparency about uncertainty. It must be acceptable, even celebrated, for scientists and agencies to say we do not know. Science is not about having all the answers, it is a process of asking questions. The public is intelligent enough to understand that. A statement like, "This object is behaving in a way we have never seen before. Our current theories are struggling to explain it, and here is what we are doing to find out more," is infinitely more effective and trust-building than silence. It invites the public into the process of discovery. Second, we must engage with speculative ideas openly. When the public or even credible scientists raise speculative possibilities, even possibilities like alien technology, the response should not be ridicule or silence. The response should be science. The scientific method is the most powerful tool we have for sorting truth from fiction. Instead of dismissing an idea, engage it. That is an interesting hypothesis. If this were a piece of technology, we would expect to see A, B, and C. Instead, we are seeing X, Y, and Z. Therefore, the data does not support that idea. This approach respects the question, educates the public on critical thinking, and demonstrates that all possibilities are being systematically checked. Third, we need real-time data access. In the 21st century, the model of hoarding data for months or years until a paper is published is obsolete. The data from our telescopes, especially those funded by the public, should be made available to the global community as quickly as possible. More eyes on the data means more minds working on the problem. An amateur astronomer, a data scientist, or a university professor in another country might see the one thing that the primary team missed. We should be crowdsourcing the universe. This open model leads to faster, more robust, and more creative science. Underpinning all of these points is one central theme: respect for the public's intelligence. The old top-down model of communication, where an elite group of experts hands down answers to a passive public, is dead. The public is now an active participant. They are curious, they are connected, and they are passionate. They are not children who need to be shielded from the complexities or uncertainties of science. They are the stakeholders. They pay for these missions. They are partners in this grand adventure, and they deserve to be treated as such. This leads to the final call to action. This is a call to you. You must demand more. Do not settle for silence and ambiguity. Demand transparency. You, the public, the viewer, the citizen, have a right to this knowledge. The exploration of the cosmos is not the private property of a single agency or government. It is the shared inheritance of all humanity. The questions raised by objects like 3i Atlas. Are we alone? What is our place in the universe? Are the most profound questions we can ask. The answers and the process of finding those answers belong to everyone. The universe is speaking to us. You have the right to hear what it says. Comet 3. i.e. Atlas is leaving us. It is now on its long, silent journey back to the deep dark, that cold, unimaginable space far beyond the orbit of Neptune. Its fiery, brief appearance in our skies, a spectacle that captured our hopes, is now over. It came to us like a traveller from a distant, unknown country, offering a momentary glimpse of a place we will never go. Now its visit has ended, and it recedes, growing fainter with every passing second, heading back to the void. This comet was always more than just a tumbling ball of ice and ancient dust. For those who watched it, felt like a gift. It was a chance, a puzzle. You could think of it as a message in a bottle tossed into the cosmic ocean billions of years ago, finally washing up on our shore. It carried within its frozen heart the secrets of the Oort cloud, the raw, untouched materials from the very dawn of our solar system. It was a piece of history, a frozen fossil from the time before planets that just happened to cross our path. It offered us a chance to look back at our own origins, to study the building blocks of our world, And so as it fades, we are left with the final necessary question. Did we read the message, or did we just stare at the bottle unopened? As this rare visitor disappears from our most powerful telescopes, we must wonder if we truly learned anything. We saw it, we catalogued it, we gave it a name, and we measured its path with our equations. But did we truly see it? Did we grasp the opportunity it presented? Or did we let this fleeting chance simply drift away, lost in the noise of our busy world, in the slow gears of our committees, and in the comfortable institutional silence that often greets the unexpected? It is a heavy, lingering thought. Did we, through our own inaction, let the messenger pass by unheard? Perhaps in the end, the answer to our question does not matter. Whether we unlocked a new scientific truth or simply missed an opportunity, the journey of 3i Atlas reminds us of something far more profound. It is a reminder of scale. It shows us that the universe is vast, endlessly mysterious, and impossibly old. We are by comparison so very small living, our fast lives on a tiny blue dot in an ocean of absolute black. The comet was a whisper from that great silent unknown. It was a faint cosmic sigh, a reminder that there are magnificent, terrifying, and beautiful things moving all around us all the time, whether we are paying attention or not. And now it is gone, returning to the silence.